finally, chapter 7.3, partial fractions. So the goal of this last chapter, the last chapter of our unit, as well as for our class, is to learn how to decompose rational functions. So what exactly does that mean, though? It's going to involve some of the stuff that we went over with systems of linear equations, but it's going to look a little bit weird. It has a lot of relation to some stuff that you'll see if you go on to Calculus 2, for example, however. But for right now, it's gonna feel a little bit complicated, a little bit convoluted, but hopefully not too bad. So what is a partial fraction decomposition to begin with? The goal of partial fraction decomposition is to separate or decompose a rational function into a sum of simpler rational functions. So for example, 8x plus 7 over x squared plus x minus 2 can be rewritten as 3 over x plus 2 plus 5 over x minus 1. So we've got this sum of simpler rational functions. What makes them simpler? Well, there's less going on in their denominators for the most part. So these two are equal to each other. But why are they equal? So let's work our way backwards for a moment. I'm going to factor the denominator on the left side. It ends up being x plus 2 times x minus 1, which should look a little bit familiar, right? It's the same denominator, so that's probably related. Now, if I take these denominators and I find a common denominator in order to actually combine our fractions, because that's the only way to actually add them together, well, I'm going to multiply 3 over x plus 2 times x minus 1 over x minus 1 and 5 over x minus 1 times x plus 2 over x plus 2. So when I do that, I'm just going to leave the denominators in factored form, but the numerators become 3x minus 3 plus 5x plus 10. When I actually add those together, 3 plus 5, that's going to be 8x. Negative 3 plus 10, that's 7. So indeed, these are equal to each other. So this is the decomposition, though. How did I get there? I can see how I can work my way backwards, but how do I get there in the first place? Well, that's the question of this whole chapter. How do I decompose? So first, we're going to start with the simplest form of decomposition we have, which is when we deal with a denominator with non-repeated linear factors. So if we have our polynomial over polynomial, our rational function, p of x over q of x, if our denominator, q of x, is equal to just multiples of linear factors and there's no repeat, so x plus 2 times x minus 1 times x plus 7 times 3x plus 14, whatever, there's no repetition there and they're all linear equations, then we get the following. We decompose into a sum of numerator is just a number, no x's or anything, just a number over each linear factor that made up our denominator. But how do we actually do the decomposition? Well, I'm going to read out the steps for us first, and it's going to sound, again, very complicated, but once we actually do it, it'll make a little bit more sense. So bear with me here for a moment. First, we will use a variable for the original numerators, usually a, b, c, d, etc., but since I didn't know how many variables I would need here, because I'm just using it in general, I've used a1, a2, a3, etc., up to an, just for generalness. So those are all of our numerators. They're just a number. Our denominators are then going to just be each factor that made up q of x, so each of the linear factors of q of x. Step 2 is going to be where we will multiply both sides of the equation. Now remember, these numbers are filled in, but these are not. And our goal is to figure out what are those numerator numbers. So we will multiply both sides of the equation by the common denominator. The common denominator will be q of x. If your common denominator is not q of x, then you're doing something wrong. So we multiply both sides by q of x. This is basically going to remove all fractions from the problem. So we'll just be working with, after some cancellation, we'll just be working with equations. They're not going to be linear equations, but you'll see that they have a relation to linear equations in a moment. So we will then expand the right side of the equation and collect like terms, and set the coefficients of those like terms from the left side of the equation equal to those on the right side, and solve for those numerator numbers that we didn't know. So again, I realize this sounds very abstract and nonsensical, but hopefully once we put it into action, it'll start to make a little more sense. So here we have an example. We've got all of our steps. We're going to try to decompose 3x over x plus 2 times x minus 1. So step 1 is simply to write out the decomposition with our unknown numerators. So that'll be some letter, a, over each linear factor. So here we're already nice and factored, so I don't have to go through the factoring step at least. If it wasn't factored, we would have to factor the denominator. You do not need to factor the numerator. In fact, if you do, it's a wasted effort because you'll have to unfactor it later because we need the numerator multiplied out in order to do this. Okay, so I go on, I write out my a over x plus 2, b over x minus 1. So I've got a sum of, I have part of my decomposition already done. Now my goal is just to figure out what are a and b. Well, my next step is to multiply both sides of the equation by the common denominator. The common denominator just being, in this case, x plus 2 times x minus 1. So I have multiplied on both sides. So that means multiply every single equation by that denominator. When I do this, it's going to cause some cancellation. So notice that, in fact, everything cancels on the left side. That's the goal. It should all cancel on the left side. But in this case, only one of each is going to cancel. Oops. This one does not cancel. This one cancels on the right side. So we end up with x minus 1 times a and x plus 2 times b. And then just 3x on its own on the left. So 3x equals a times x minus 1 plus b times x plus 2. Like so. Next, I am going to take this and expand the right side of the equation and collect like terms. In other words, I will multiply my a in, so I get ax minus a, bx plus 2b, and then I combine like terms means I pull my a and my a's and b's together when they are next to x, and then my numbers that are not next to an x, those are also going, my constant terms are going to be pulled together, and then we kind of separate them into parentheses, etc. So I'm getting ax plus bx becomes a plus bx, and then negative a plus 2b, that's all together over here. These are my coefficients. My coefficient of x on the right side is a plus b. My constant term on the right side is negative a plus 2b. Because remember, these are just numbers. A could be 1 and b could be 2. And so then we just say the coefficient of x is 1 plus 2, which is 3. That's what we're talking about, is the a and b represent numbers. And so the coefficient of x is just whatever number their addition represents. So to actually finish out this problem, I have to set the coefficients of the like terms from left side of the equation equal to those on the right side. 3x is on the left, so 3x has to be equal to whatever the coefficient of x is on the right. So 3 is equal to a plus b. There's no constant term. This is like saying 3x plus 0. So there's no constant term, so we say 0 equals negative a plus 2b. And would you look at that? We have 2 equations and 2 variables. That's something we know how to deal with. So we can solve. We have more than one way to do this. We can do substitution, we can do elimination, whatever your favorite is. I, in particular, am going to do elimination here. So when I do elimination, I add these. I'm going to get 3 equals 3b. And then I divide, so I get 1 equals b. And then I can plug back in, so I get 3 equals a plus 1. And then 4 equals a. And there's plenty of other ways you can go about this. Oh, oops. Geez, I can't subtract. 2 equals a, because we subtract 1. Wow, okay, so 3 minus 1 is 2. So a equals 2. And this is why we check our work. Because if I had said 4 equals a, I could very easily go back and say, well, 4 plus 1 does not equal 3, and then I would very much know that I did this wrong. So it's always good to check your work. I make mistakes too. So we have b equals 1, a equals 2. I can check this. It will work. And so I can then state my final answer is going to just be replacing this like so. But there is an alternate approach, and I'm just going to show it. This only works in this condition. All other conditions we're going to look at, this alternate approach will not work, but it does make this way a little bit quicker, so I'm going to show it. Feel free to ignore it if it makes no sense to you. The alternate approach is solve for a and b by plugging in the zeros of the linear factors. Again, the reason this works is because we are working with non-repeated linear factors. In the future, won't work because there will be repetition or there will be nonlinear factors. So, I've multiplied it out. I still have this same thing right here, but instead of multiplying my a's and my b's in and collecting like terms and all of that, I'm plugging in values for x. So if I plug in 1, that's going to eliminate a. Like so. And so then I will get 0 plus 3b equals 3, so b equals 1. And then I plug in here, I'm going to plug in negative 2. That's going to get me negative 3 times a plus 0 equals negative 6. And then I can solve for a and get a equals 2. So that it can be a little bit quicker to do it that way in only this example. So like if you're not working with non-repeated linear factors, then you can't do this, and so if it confuses you, don't use this method. Anyway, either way, we get the same answer, and our final solution looks like the following, where I just replace my a and b with the two numbers I got. Make sure you're replacing the right ones, like a is 2 and b is 1. Make sure you do it in the right order, because it does matter. Now, from here we have several other types of factoring that can occur. So that was the non-repeated linear. X plus 1 times x minus 2, or whatever, where it's all this, they're all linear factors and there's no repetition. But what if there is repetition? So here, if we're getting repeated linear factors, then things get a little bit more complicated. Essentially, we, for each repeated linear factor, so here I have a repeated linear factor, I have to have an added rational function for each degree that this factor exists for. So if we have x plus 2 cubed, then I'm going to have a over x plus 2, b over x plus 2 squared, c over x plus 2 cubed. So you get one per each, counting up until you get to the actual whatever that degree is, whatever that exponent is. So for example, here I have negative x squared plus 2x plus 4 over x cubed minus 4x squared plus 4x. I factor the denominator, so in this case it's as if it wasn't given to you factored. I factor the denominator, it ends up being x times x minus 2 squared. Since x minus 2 is squared, is to the second power, we include fractions with denominator x minus 2 to the first and to the second. So we get a over x right here, but then a over x minus 2 and a over x minus 2 squared. If it had been cubed, we would add another one, x minus 2 cubed. If it had been to the fourth, we'd add another one. Just keep counting up until you get to whatever number this power was. So we just have to add each of these in every time. And then we go through and solve in the same way as we did before. So I will briefly go over the steps to doing this, but it is the exact same steps as before. Again, that alternate solution method does not work, but all the other steps do work. So I just go through, I multiply by my common denominator. So when I do this, I'm going to end up with, let's see, there's not a heck of a lot of room here, but we will get negative x squared plus 2x plus 4 equals a times x minus 2 squared once it's canceled out. B times x times 1x minus 2, and then c times just x. So again, we're multiplying by this, and notice that the x minus 2 squared will cancel from the c, only one of the x minus 2's will cancel from the b, and only the x will cancel from the a. So we get the following. Then I multiply it out, and make sure you're paying attention to the fact that this is squared. This will get us a times, let's see, x squared minus, this will be 4x plus 4. Then I'll just do this. Bx squared minus 2bx plus cx. So this is ax squared minus 4ax plus 4a plus bx squared minus 2bx plus cx. Okay, and we keep going. So from here, we will combine our like terms. So combining like terms will get us a plus bx squared, and then plus negative 4a minus 2b plus c, remember there's that third one there, x, and then finally plus 4a as our final sort of lonely constant term. All of this is still equal to that. And so when we build our system of equations, again, I didn't give myself a heck of a lot of room to sort of go through this example. We will get coefficient -1 is next to the x squareds. So next to the x squareds is a plus b. So -1 equals a plus b. Then 2 is equal to -4a minus 2b plus c. And finally, 4 is equal to 4a. So luckily, this equation makes things a little bit easier. We can solve that. A is going to be 1. Then we plug that in. So a equals 1. Then we can plug into here and get, if a is 1, then b will end up being -2. And then we plug in again and we can find c. I'm not going to go through all of the steps of these because it is just the same stuff we went over in chapter 7.2 once again. We're working with systems of equations now in 3 variables. It's the same steps as we've continuously gone over, so I will sort of give you ideas of how to break down these partial fractions, but I'm not going to go through the solving steps. I will gladly do that in office hours or if anyone has any questions about particular examples like on the lab, etc. But for the purposes of the video, I'm not going to go through all the solving steps here because, again, you can just go back to chapter 7.2 and review that for how to solve them. All right. The next type of decomposition we can run into is non-repeated irreducible quadratic factors. So, here, if I have an irreducible quadratic factor, just a single irreducible quadratic factor, or multiple of those, but the point is there's no repetition of them, then my numerator is no longer just a single number. It's now going to be linear. My numerator will be ax plus b instead. So, you might get multiple of these, but essentially, you can kind of see there's a little bit of a pattern forming. We're not going to go super far with this, but you'll see in, for example, when this comes up again in calculus, you'll see that you can continue this pattern into the future where you will see if there is an irreducible cubic, then irreducible meaning it does not factor. That's what irreducible means, is we can't factor this, at least not with real numbers. If there's an irreducible cubic, then we'll have an x squared term on our numerator. If there's an irreducible fourth power, then we'll have an x cubed term in our numerator, etc. So all of that is something we can think about. So anyway, again, the steps are exactly the same, so I'm not going to rewrite it, as long as you just note the new thing we have to add in. So for example, if I have 8x squared plus 12x minus 20 over, and this time I've taken the time to have factored it for you, So x plus 3 times x squared plus x plus 2. X squared plus x plus 2 does not simplify. You cannot factor this using real numbers. So this is a non-repeated, because there's only one of them, irreducible quadratic. And so when I break it down, it will be a over x plus 3. So this stays the same as it's been. We're still following that same pattern. But then bx plus c over the quadratic. And then I do the same exact steps. So I multiply by this common denominator. When I do so, I will end up with 8x squared plus 12x minus 20 equals a times x squared plus x plus 2 plus bx plus c times x plus 3. Make sure you're paying attention to your parentheses here. If you lose your parentheses and don't multiply this properly, you will get very wrong answers. It will be points off. Make sure you're actually writing this in parentheses. X plus 3 is getting multiplied by the whole quantity bx plus c. I get this. I see mistakes of this a lot, so that's why I'm making a big point of saying it. Make sure you're using parentheses. So then we're going to get ax squared plus ax plus 2a is plus bx squared plus 3bx plus cx plus 3c. And so our system of equations will look like the following. 8 equals a plus b. 12 equals a plus 3b plus c. And negative 20 equals 2a plus 3c. And again, so this one's not quite as simple, but at least all three equations don't actually have three variables, so it does make it a little bit quicker than most of the stuff we went over in chapter 7.2. So we go through the steps of solving to figure out what a, b, and c are, and then you can complete the problem. Once again, I'm not going to go through this, just go back to chapter 7.2 to see the steps if you're rusty on how to do that. And of course, if you have questions and you want my help, I will gladly go over it. The final type of decomposition we're going to look at is decomposition with repeated irreducible quadratic factors. So now I have that irreducible quadratic, but now it's to a power. So it's that x squared plus x plus 2 all cubed or something like that. So just like we did with the repeated linear factors, this just means we're going to have to count up. So we get that irreducible, the first power, the second power, third power, fourth power, up to whatever the power was. And then we get ax plus b, cx plus d, ex plus f over each of these steps. So, for example, if I have x to the fourth plus x cubed plus x squared minus x plus 1 over x times x squared plus 1 cubed. This is already factored for us. X squared plus 1 is irreducible with real numbers, so we get a over x, then bx plus c over x squared plus 1, dx plus e over x squared plus 1 squared, fx plus g over x squared plus 1 cubed. And this is a very mean one, so I'm not going to go through how to do it because it would take a lot more room than I've given myself, because there's 1, 2, 3, 4, 5, 6, 7 variables here instead of the usual up to 3. So at most I would make you do four variables. That is entirely a possibility that you might have to do four variable equation. Still works the same way as 3. It's just another letter in there. But I'm not going to make you do a 7 variable version. This is just for an example. That's why I'm not going to go through all the steps. But in summary, this is basically how things work. So if we have a factor in the denominator that is linear, we get a term in the partial fraction decomposition that is just number over that factor. If that linear factor has a power to it, then we get number over that factor to each power counting from 1 up to that power. So a over linear factor, b over linear factor squared, c over linear factor cubed, up to whatever this k value is. If we have a quadratic factor, we get ax plus b over the quadratic. If the quadratic factor is to a power, then we count up to that power as well. And again, you can see there's sort of a pattern here. If we were to go further, we're not in this class, but you'll see it in calculus, that if there were a cubic factor, we would then have ax squared plus bx plus c on the top. And if that cubic factor were to a power, then we would have one for each power. If it were the fourth power, etc. It's a pattern. So if you can remember the pattern, that should help establish what's going on and help you remember. But remember, my last thing for really this whole unit is it's very easy to check your answers in this unit. So please make a habit of doing so. When you get an answer, plug it back in and make sure it actually works. Make sure the numbers you're getting make sense. If you show me you plugged it in and maybe you make a mistake when plugging it in and you get that it works, I'm probably going to mark you almost entirely correct because at least you did that step. Because mistakes happen. You are not perfect. I make mistakes all the time. So please check your work. Don't just trust your answers blindly. And I guess that is my last tip for this whole unit, this whole chapter, this whole class in general. So hopefully we're ending on a not too painful note, even though this chapter is a little bit weird, but overall this unit is, I've been told, not too bad, so hopefully this stuff is at least a little bit familiar and that should help sort of ease us out of class.